Part 2. Refining Assumptions in the Energy page. In the previous part of this video, I did a pre-feasibility analysis of a 20 megawatt photovoltaic project proposed for northwestern Mexico. I used the Virtual Energy Analyzer to rapidly access a set of reasonable default values for the project inputs. Now I want to revisit those inputs, particularly in the energy and cost pages. On the energy page, I previously used a level 1 analysis and assumed a capacity factor of 19%. Was that a good assumption? Let's find out by doing a level 2 analysis, where we will calculate the capacity factor based on inputs describing the climate and the project. First, though, a note of clarification. The parameters entered under this level 2 analysis are completely independent of those used previously in the level 1 analysis. For example, I set the initial cost to $1,400 in the level 1 analysis, but when I switch to level 2, it remains at $2,800, the value proposed by the Virtual Energy Analyzer. I can switch back and forth between level 1 and level 2, and the changes I make in one level will not affect corresponding cells in the other level. In level 2, the top part of the energy page is where the orientation of the photovoltaic arrays is specified. I told the Virtual Energy Analyzer that the arrays are to be fixed in place rather than tracking the sun, and that is reflected in this solar tracking mode cell. The Virtual Energy Analyzer has set the slope to 31 degrees. This was chosen based on the latitude of the site. A slope equal to the latitude generally maximizes annual solar collection. In reality, however, I might not want the slope to be that high. For a large array composed of rows of subarrays running east to west, the rows must be spaced far enough apart to avoid significant shading of the modules by the row in front. A more steeply tilted array leads to the top of the array being higher, and the higher the array, the more widely spaced the rows must be to avoid shading. To keep land utilization down, we might choose a lower tilt angle. I'll set this to 25 degrees. The azimuth refers to the geographic direction that the front of the array faces. By clicking on the word azimuth to open the help, I can access a diagram that shows that RETScreen considers due south to be 0. This is ideal for Northern Hemisphere projects such as this one, so I'll leave the cell at 0. Clicking on the down arrow next to Show Data, I can see why RETScreen had me enter this information. For each month, the daily solar radiation on a horizontal plane is shown. This, it can be seen, is copied directly from the climate data on the location page. Our array is not horizontal, however. RETScreen has applied an algorithm that supplies estimates of the daily solar radiation on a south-facing array tilted at 25 degrees. We can see that tilting up the array increased the total solar radiation incident on the array over the course of the year. If you are interested in understanding better how RETScreen calculated the solar radiation available at this tilt angle and orientation, you can consult the Engineering EText book, which can be downloaded through the link of the same name on the Help screen on the File page. It documents the assumptions and algorithms used in RETScreen. The next part of the energy page is where the equipment is specified. The main component of a photovoltaic project is the photovoltaic module. At the time I'm recording this, most cells in photovoltaic modules are fabricated from wafers of polycrystalline silicon. I'm going to assume that my project uses these commonly available modules and pick Poly-Si from the drop-down list of different technology types. This hypothetical project I have in mind is a 20 megawatt project. The 10 megawatt I find in the power capacity cell is the capacity of the nearest photovoltaic project archetype available to the Virtual Energy Analyzer. I could simply overwrite this value with 20 megawatts, but I can also pick a module from RETScreen's database. I open this product database by clicking on the shopping bag icon at the right. Note that at the top of the dialog box that opens, The technology type is polysilicon. As a consequence, in the drop-down list of manufacturers, I only find companies that have poly-Si offerings. I'll pick a large 310 watt module from Canadian Solar. By changing the number of units to 64,516 modules, I end up with a nearly 20 megawatt array. The information box indicates that these modules are 16% efficient. When I click on the Paste Data button to close this dialog box, this efficiency, as well as the manufacturer, model, and number of modules, is copied to the analysis. To keep my numbers round, I'm going to set the array to exactly 20 megawatts. The normal operating cell temperature and temperature coefficient were set by RETScreen when I selected poly-Si as the technology type. These two parameters dictate how temperature affects module efficiency. I'm going to talk a bit more about them in part 3 of this video. RETScreen indicates that the area of the array is just under 124,000 square meters. Note that this is not the land requirement, which will be much larger, but just the dimensions of the array if all the modules were laid out touching edge to edge on a big horizontal surface. To this point, we've provided RETScreen with parameters that permit it to estimate how the orientation of the array and the site temperature affect the plant output. But there are other factors that affect the array performance, and, unfortunately, they generally decrease the plant output. The combined effect of these other factors can be included in the miscellaneous losses cell. Help tells us that this is where we might include losses due to dust or dirt, mismatch between the electrical characteristics of interconnected modules, or the resistance of wiring. I think that with judicious plant design and O&M, I can hold these to 10% for this site. The inverter is the device that converts the direct current output of the array into the alternating current that can be fed onto the grid. Modern inverters are remarkably efficient, particularly for large units. I'll put in 98% here. For a big project such as this one, the inverter capacity is typically around 20% smaller than that of the array. Yes, for a few hours of the year, the photovoltaic array will generate a bit more power than the inverter can handle. And during those hours, the inverter will waste that small portion above its maximum input rating. But in compensation, the cost of the inverter is reduced by around 20%. I'll assume an inverter capacity of 16 megawatts for this 20 megawatt project. There is a miscellaneous losses cell for the inverter too. This covers any losses in power electronics and in the connection to the grid. I'll leave the estimate of 1% alone. This might cover losses in a step-up transformer. With that, RETScreen has all it needs to calculate the capacity factor. In part 1 of this video, I assumed that this value was 19% and entered that directly into a level 1 analysis. Careful consideration of my assumptions has suggested that my project's capacity factor will be around 20.6%. Some of you familiar with photovoltaic projects in sunny climates may find this capacity factor to be lower than the numbers typically cited. There could be a number of reasons for this, but the likely culprit is that RETScreen calculates the capacity factor on the basis of the DC or array capacity, whereas the capacity factor that is cited for large projects is often calculated on the basis of the AC or inverter capacity. Recall that the capacity factor is defined as the average output of the system expressed as a percentage of its rated capacity. If we use the inverter rating as the rated capacity of our system, and our inverter is 20% smaller than the photovoltaic array, then our capacity factor will look a quarter higher than what we find in RETScreen. For this project, the AC capacity factor would be just under 26%. RETScreen's use of the DC capacity factor has some compelling advantages. Note that the AC capacity factor can be inflated simply by using a very undersized inverter. The high capacity factor doesn't mean that the project performs any better. Indeed, it will likely produce less electricity, but it does look more attractive. At the bottom of the energy page, we get to the initial costs and the O&M costs. I'll set those to the values I used in part 1. 1,400 Canadian dollars per kilowatt, and $17 per kilowatt per year. Those of you familiar with photovoltaic projects may at this point ask how to account for annual degradation in the photovoltaic module output. Typically, in a hot environment such as this one, there will be degradation of 0.4 to 1% per year as the module ages. There is no input explicitly for this in RETScreen, but we can still take it into account where it matters most, in our financial analysis. Year on year, this degradation reduces the revenues from electricity sales. To reflect that, I can decrease the electricity export escalation rate from 3% to, say, 2.3%. Keep in mind that while this corrects for degradation when looking at the principal financial indicators of net present value, internal rate of return, and equity payback, it is not reflected in the energy production cost or the GHG reductions over the life of the project. With that, I've completed a slightly more detailed analysis of my project's expected performance, but I haven't yet explored the impacts of any design choices. I'll do that in the next part of this video when I compare the financial viability of different module types.